Hey, Justin. Hey, Esther. Hmm. Hey, Rosie. Hey, Aaron with exclamation point. Hi, hi, hi. Oh, I'm blocking the do now. Holy moly. Holy moly. Hey, Aiden. Hey, Sumaya. Thank you guys for tuning in on time. Right at 11. For everybody else, let's start the do now, right? So basically, I'm generating periodic waves just by holding a string. My friend's holding the other end, so it's taut. All right, and all I'm doing is I'm just shaking it back and forth at a specific frequency. My hand right now would probably be 2 hertz. Okay, if I do it like this, it's like 3 hertz, right? This is like 1 hertz, right? So what I'm saying is, well, what happens, looking at this formula, what happens to V and lambda if I increase the frequency of my shakes? All right, so if I go from like this to something like that, what would I expect to happen in the string? Like, what differences would I observe? Write that down. Don't put it in the chat, right? There you go, Oliver. Good morning. Hey, Allison. Sorry. So we got 2 more minutes left. If you haven't already, let's start to do now. Okay? Yes, Gallagher. Sorry, Alex. I'm just really tired right now. I slept at 5 o'clock. I just couldn't sleep. I was writing, and I couldn't stop writing, and I never got sleepy. Anyways, what's your... Oh, God. Oh, I need more tea. BRB. Oh, Alex, sorry. I guess the answer is yes. I thought I responded. Alton, good morning. Meg, hey. Who else promised me in an email that they would start attending more live streams? Who was that? Jennifer Lee, you in the chat? Huh? Hi, Alexi. What's up? I got no sleep. That's what's up. What's also up? We got a double length lecture today because we got screwed yesterday. Today. We have a double length lecture today because we got screwed yesterday. Okay. So, let's go over this problem. No, it's really not double length. No makeup. The lecture today is the exact same one I had scheduled for yesterday. All right. So we're not going to overload on the stuff. Okay. Yeah, let's get started. So here's the big problem. Okay. I have a string. My friend is holding it on the other side to keep it taut. And all I do is I just shake it at a regular frequency, and I produce these waves, right? The waves travel with some speed v. If I measure that, then I can actually predict the wavelength I get just by solving for wavelength when I plug in my v and the known frequency, right? So this is like 2 hertz. 1, 2, 1, 2, 1, 2, right? 1, right? And let's say I increase the frequency to like 3 hertz. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? So, well, let's predict what happens. Let's use this formula. I increase frequency. Uh-oh. There are many things that can happen. This could stay constant. This could increase. This could stay constant. This could increase. They both could increase. This could decrease. But this increases so much more than this decreases. This could increase. Like, right? There are a lot of different combinations of what can be happening here, right? And this do now is to really test your understanding of not how to plug and chug, right? If I give you V and F, can you solve for lambda? If I give you lambda and F, can you solve for V? It's not that, right? It's actually interpreting what's going to happen. What happens? V is constant. V will not change. Who can tell me why velocity of the wave won't change? And if you guys need a reminder, remind yourselves and ask yourselves, what does velocity of a wave depend on? The speed of any wave traveling in any material depends only on one thing. The medium, not median, right? The medium or the material, right? And when I shook it, and I shook it more vigorously, I'm not really changing the actual material, the rope, right? All I'm really doing is just changing the frequency. So because the medium and the material didn't change, V was constant. Now I can say absolutely what happens. When my frequency goes up, my wavelength will go down, right? So it'll start looking like, right? Where these were the old waves, right? And then these are the new waves. Like this represents like the point where I started shaking more vigorously, right? And the cool thing is that the distance from this peak to this peak will always remain the same, right? Why? Because these peaks are traveling at the same speed. Now you can kind of see why it wouldn't make sense if the speed changed, right? If the waves that I send ended up getting faster, that would mean this wave would catch up to that wave, which would make no sense. Like that, we don't see that happening, right? Okay. Let's move on then to the weird stuff that happens if that actually did catch up to that. I want to look at the situation where waves actually take the same location. Okay? Justin, what's wrong? Why'd you say shoot? Justin, are you okay? Yeah, it's fine. Don't worry about it, okay? So, oh God. Excuse me. Just give me a sec. All right, here we go. Here's the situation. Okay? I am standing right here. My friend is standing right here. And we have a rope in between us, right? And I'm trying to do a physics demonstration for class. So I'm about to shake the rope, okay? So I shake it once, and I send a pulse through it. That's it. That's all I do. I just go like this. I don't go down. I just go up. So I send one little hump through, okay? My friend, because there was a miscommunication, does the exact same thing. And she sends a thing coming towards me, okay? So now we have two waves headed towards each other, okay? And if this is drawn to scale, let me assume that this wave is like 50 centimeters high, and this one is like 60 centimeters high, okay? Something really interesting happens. So at one point in time, it looks like this, but eventually they will collide. Okay, good morning, Tim. Eventually they'll collide, and there are a lot of student predictions to kind of like what will happen. Some say they bounce, right? Some say they pass through each other. You have good reasons for thinking both happen, but I'm going to tell you right now that the answer is they pass through each other. And so it's really hard to tell because they kind of, whether they pass through each other or they bounce off, it kind of looks the same, right? Because you basically have two waves going there and then two waves coming out. So this is why I made this hump taller, because once it passes through, the taller hump will be here and the shorter hump will be there, right? Just opposite that. But the more important thing is what happens in the middle when they actually occupy the same space. Because my rope is at an impasse. This wave is telling my rope to behave like this. And then this rope is telling my wave to behave like this. What shape does my rope take? It's actually quite simple. It's not the average, okay? You just add them together. So what you end up having is at this very special time where they completely overlap, you get a 110 centimeter tall wave. Whoa. That's all you do. Easy. That's the lesson. Bye. Just kidding. All right. Kind of. Right. The only topic we're going to learn today is interference. Okay. And interference is simply, here's how I define interference. When multiple waves occupy the same space. Right? Like when I had those two pulses occupying the same point in the rope, well, how does the rope behave? Okay? And the answer is simple. All you do is you add the displacements where they overlap. The key is where they overlap, okay? So a very classic example is a square-shaped wave two square-shaped waves, right? So I'm just going to draw like what happens as they get closer and closer together. Right? Now, basically, I divide, like, this is the point they just come into contact, right? Now, as soon as, so I will call this, right, maybe this is 1 meter, and then this is 2 meters, okay? So what I'm saying is this is now 4 meters long, right? Because this is 2, this is 2, this is 2, this is 1, right? Now, so at this point, there's no overlap, right? Both the pulses are just completely touching each other. And what comes next is now I finally have some overlap. What happens at that overlap level? Now I have a 2 meter high wave, right? That's 2 meters high, and this is like 3.5 meters, right? Right, eventually, I'll have a 2 by 2 square, right? This is the point where they completely overlap, right? And then it'll do the reverse. Right? And they keep going, right? So interference only happens where they overlap, right? So that only occurs like in these sections here. Like here they barely overlap. So how much are overlapping? I would say, yeah, like a quarter of their length, right? All right. Any questions with this so far? Cool. Interference, you gotta know, also acts in the reverse way. Like if I sent these two pulses together, whoa, all right? What do you think happens? So this is right when they touch. What do you think happens when they completely overlap? One part of the rope wants to look like that. The other part of the rope wants, the other wave wants the rope to do that. What do? I add them. So what do I get? Flat. So there is one point in time, and one point in time exactly, right, where these two pulses overlap perfectly, and the rope will be completely still, right? They cancel out, yeah. With the practice today, I'm going to be sending out a video of interference, especially in the ocean. It's so cool, all right? Please take the time to watch it. Yeah, and then afterwards, it'll look like that, right? So this bottom thing keeps going to the left, this the top thing keeps going to the right. The most important thing about interference is related to this concept in physics called superposition. We learned this about electric fields, right? What that means is the position and the velocity and the all the qualities of one wave are completely independent of the other one, right? So this wave never interacts with that wave, right? They don't bounce after they pass through. It has the same velocity that it had before. This one has the same velocity it had before. This one has the same amplitude it had before. This one has the same amplitude it has before, right? They don't interact in any way. They don't affect each other in any way. Which what I mean by that is, like, if I made this twice as big, right? It wouldn't affect the behavior of the leftward traveling pulse at all. What it does affect is the interference pattern, right? If this was 2 meters high and this was only 1 meter deep, when they overlap, it would actually create a 1 meter high bump, right? Because I'd have like a 2 meter high thing, and I have to add that to a negative 1 meter high thing, so the interference would actually give me just a 1 thing, okay? Cool. It means they ignore each other, right? So the pulses don't affect each other, but when they occupy the same space, like, they're gonna still behave the same way. Which what I mean is, like, hey, when these are overlapping, this bottom pulse is still gonna act like the same 2 centimeter wide, 1 centimeter deep bottom pulse that it was at that point in time. These pulses are the same. Its velocity is the same. This top pulse is the same as it was at that point. Nothing changes because this other pulse is there. Things do change, but the pulse itself is not changing due to that pulse. What is changing is the behavior of the string, because now the string is torn between two modes of existence, right? Like, the string wants to do that and it wants to do that at the same time. What does it do? It just does both, so it adds them together, okay? Timothy, well, you'll have a problem with that. Yeah, you'd still add them. It's no big deal, okay? And what this means is, the reason why I didn't do a sinusoidal example here is it's really hard to, so if I have a sinusoidal wave here and a sinusoidal wave here, it's really hard to add this overlap because it's constantly changing. So I don't want to do that. It's much easier to do with squares. Cool. What was I going to say? Okay. This is called constructive interference. This is called destructive interference. Okay. Destructive interference doesn't mean I have a downward thing or a negative thing. It means I have opposite things, which is to show you that if I have a downward pulse and a downward pulse, they will constructively interfere to make a really big downward pulse there, right? So constructive interference means I have two things with the same polarity, and destructive interference means I have two things of opposite polarity. And it means, like, when they intersect, the amplitude of the interference will decrease. Constructive interference means the amplitude of the interference will increase, Okay. You didn't learn the formula to look at moving pulses. Okay. You learn how to do it for an instant, right? When it looks like that. It's not what we're doing. Okay. Cool. So your homework is basically going to be a worksheet where you have to like draw the interference pattern or like the shape the wave will take when I have two waves in it, right? I'm going to post that. I'm also going to post a really cool video about interference with ocean waves. Please watch it. And with that, I will say have a great Tuesday. Short lecture, huh? Cool. Bye. Have a great day.